Welcome back, everyone. We're getting close to the end of the semester here. A couple announcements. I uploaded homework 7 last night. It's just one problem. Hope it shouldn't be too much of a hassle. Um, that's due the last day of class, along with anything else that needs to be submitted if you haven't submitted it. Um, Specifically, final project, the peer review peer evaluation form for the final project, and the homework 3 regrade. If you wanted to resubmit homework 3, that's due August 12th, 11:59. Um, if it's late, I can't accept it, unfortunately. Um, that's how it is. I have to get grades in by 3 days later, so get everything in on time, and we'll all be happy. Um, Spot reviews are still available for a few more days. I think they close on the 12th, like everything else. Please, please, please do those. It'll help me a lot. Teaching is something I'm new at, but it's something that I want to be, I want to improve upon. I want to get better at. Um, so your feedback is really helpful um, in that respect. I want to hear it. I want to read it, and I want to see how I can improve. With that out of the way, let's get into the content. So we're going to talk about one way that we solve integer programs and why integer programs are or can be problematic compared to linear programs. And branch and bound is probably the most important way that we solve integer programs. Um, yeah, and we'll talk about it more in depth. We'll get into some more of the theory behind it in DOR2 if you end up taking that. But today we'll just do an example and we'll talk about how it works and why it's problematic and why it's slow. Yeah. So we're going to look at an example. This comes from the Winston book. That is the typical book that this class is based on, which is not currently in print. So it's an integer program. Notice that Rx, that should be, hold on, I didn't plug in my, give me a moment. My tablet. Um, should be an I for all I in, or better yet, x1 comma x2 are in the non-negative integers. So this is the plot of the feasible region that comes with it, or associated with this problem. We notice we have our constraints are still lines in 2 dimensions. But since we're on the integers, the feasible region is not really the shaded region, it's really all of these lattice points here in the region. All of these integer points. And that poses some problems for us, because remember that the simplex algorithm finds extreme points of the greater polyhedron. And this extreme point here for this integer program is not on that integer lattice. It's not an integer point. It has the solution 3.75 and 2.25. That is actually the point that the simplex algorithm will give you, because obviously the simplex algorithm does not actually work on integer programs. It works on linear programs, continuous linear programs. So it's going to return that extreme point, which is not an integer point. And you may say, hey, what's the big deal? Why don't we just round it down to this point? Well, we can do that, and in some cases that's perfectly fine. A lot of knapsack problems, the optimal solution is just the rounded down, relaxed, continuous solution. But we see here that this point is not actually optimal, this rounded down point. We can sort of see that this is the gradient, or this is the level set, and its gradient. We can see that there's still some improvement to be made on that point. Notice this point is better. So we can probably solve this graphically for this two-dimensional problem, but that's sloppy, and it doesn't extend, again, to problems with hundreds of dimensions or hundreds of thousands of variables. So we need a systematic way of finding these solutions. Now, the book proposes two ways: cutting planes and branch and bound. I'm going to talk about branch and bound today, and cutting planes either tomorrow or Friday. So let's get to it. The first thing we're going to do is define what's called the LP. So if this is problem P, then we're going to define the LP relaxation of P. And that's just going to be very similar. And that underscore didn't disappear for some reason. 9x1 plus 5x2 less than or equal to 45. And then x1, x2 are non-negative. The only difference is that we drop the integer constraint, the integer domain. It's called the LP relaxation, sometimes the continuous relaxation or just the linear relaxation are all common phrases. So we're going to start with this. And then we're going to solve it. Now, I'm going to call this P prime. Is this whole relaxation. P prime has a larger feasible region than P. If we look at our example here, the feasible region for P is just all of these lattice points, all of these integer points that are inside of the constraints. P prime, the relaxation, includes all of those points. All of those points are still feasible to the relaxation, but there are many more points. There are uncountably more points in the relaxation, feasible to the relaxation, which means that the optimal solution of P is less than or equal to the optimal solution of P prime. In other words, P prime is an upper bound to P. Any point that is feasible to P is also feasible to P prime and has the same objective function value. So if P has a solution, an optimal solution, P prime has that solution as feasible to it, but not necessarily optimal. So again, we can look at our example here and notice that I'm not actually sure which one is the optimal solution to P here, but P prime, its optimal solution is this point 375,225, which is non-integer. So first thing we do, look at the relaxation. I have written up that problem in Python, and I figured out how to zoom in on the console. So we have that now. Might be able to see it. I just wrote up that problem in Python. This is the continuous relaxation. The true problem would have the word integer here. So let's solve that. And we see we get the same point that the book spat out. 375,225 with an objective value of 41 1/4. So what we're going to do is we're going to start with that linear relaxation. That's probably not big enough to see. Let me increase the size of this. LP relaxation. So Z, our objective is 41.25. X1 is 3.75. Next 2 is 2.25. So we have an upper bound on the problem. 41 and 1/4. We're going to note that and we're going to leave it there. Then, what do we want to do? We have two non-integer variables, two non-integer points. But we want those to ultimately be integers. So what we're going to do is branch the problem. We're going to say x. We're going to add some constraints to this problem to try to force those variables into integer solutions, into integer points. So let's do that. The first thing we're going to do is we're going to look at x1 first. Let's try to force him into being an integer. So we're going to add some constraints. X1 greater than or equal to 4. X1 less than or equal to 3. So I got those by noticing that x1 is between 3 and 4 at the moment. So we want it to never again enter that sort of space. So what I've done is I have added two new constraints. Let me do this in blue. Or red, that'll show up better. Red. I've added two new constraints. We can't enter that region anymore. Now this gives us two feasible regions, two different feasible regions. The simplex method, this is no longer convex, right? The simplex method can't handle this. So we need to solve two different LPs, actually. One for this region. This is a small, why did my brushes get so small? This is the first subproblem, and this is the second subproblem. So, we're going to have sub problem 1 has this new constraint to it. So let's solve that first. Actually, correction. Let's do this the other way around. Let's solve this one first. X1 greater than or equal to 4. So let's add that to our Python script. Bring it down here to this new section. X1 greater than or equal to 4. Solve the problem, and we have a new solution. So let's update our sort of tree here. Z equals 41, x1 equals 4, x2 equals 1.8. So problem 1. Well, we have an integer. X1 is now an integer, just like we wanted. But X2 is still not an integer. It's still a decimal. So we need to branch again. We're going to add X2 greater than or equal to 2 and X2 less than or equal to 1. So if we look back at this problem, let's change this. This is actually subproblem 1. And this is subproblem 2. Now we're going to cut out this region. But really we're only doing that, we've already branched, so we're really only doing that to the branch. So we can't enter this region anymore. And so we can see probably that one of these problems is going to be infeasible already. So let's try that. Greater than or equal to 2. Call this subproblem 2. And let's swap back over to the Python and add that constraint. And it returns infeasible. So that's not going to work. Instead, let's do the other branch while we're here. And that's our result. So subproblem 2, x2 greater than or equal to 2 is infeasible. Subproblem 3 had z equals 40.522 something. Maybe not. What was it? 4055. Repeating. 4055, etc. X1 was 4.44 repeating, and X2 was 1. Well, now, yes, that's right. Now, we again have the problem of X1 not being an integer. So, we have to branch again on X1. X1 greater than or equal to 5. X1 less than or equal to 4. So let's try X1 less than or equal to 4 first. Okay, so we found an integer solution. Excellent. Great, great, great. So let's jump back and write it down in our tree. Z equals 37, x1 equals 4, x2 equals 1. So this is candidate. I'm going to just mark that in green. We have found an integer solution. We don't know yet. Oh, this is on the just PDF. We don't know yet whether it is optimal. We found an integer solution, but it might not be the best integer solution we can find. So what we do is we write down lower bound equals 37. We found a lower bound on the problem. That could be optimal, we just don't know yet. So we continue to search through this tree. Let's try x1. Oh wait. I did these backwards. Less than or equal to 4, greater than or equal to 5. So let's try swapping out that constraint for the greater than or equal to 5 version. Greater than 5. 50 has an objective value of 40. So z equals 40, x1 is 5, x2 is 0. This is another integer solution. This has a better objective function value than we just found. So we're going to update our lower bound to 40 because we've found an integer solution that has a higher objective function value than the one we just found earlier. So that's good. There's still one, so we've branched this side of the tree to its conclusion. There's nowhere left for us to branch. We have integer solutions at both of these points. They're either integer or infeasible, and there's nowhere left for us to branch over here. So we have to look back at the x1 less than or equal to 3 side. So we're going to come back to Python, get rid of all of these, and we'll be left with x1 less than or equal to 3. Solve it. We found an integer solution right away. Subproblem 6 is z equals 39, x1 equals 3, x2 equals 3, and that's an integer solution. So we want to look at that. So now our branch and bound tree is complete. We've looked at both sides, at every possible branch, until we found integer solutions or infeasible solutions everywhere. So we're done. We just need to find the integer solution, or the optimal, the best integer solution. Well, we found that there was a lower bound of 40 here. We found a 40 somewhere, so we can see that z is or that subproblem 6 is not it because z39 is less than our lower bound of 40. And similarly, subproblem 4 had a z of 37, so that's not it. So it must have been subproblem 5. It has a z of 40. And so that's our best integer solution that we found. So the E z equals 40, x1 equals 5, x2 equals 0. Oh, I've neglected to swap us back to here, so let me repeat that. The lower bound we had was 40, so subproblem 6 had a integer solution, but its objective function was less than our lower bound, so we don't care about it. Subproblem 4, we had already decided that it was an integer solution, but it was worse than subproblem 5. So subproblem 5 is our optimal solution. Not just to the linear relaxation, but to the integer program itself. So this is what your PULP or your Excel solver does every time you ask it for an integer variable. It's going to solve an LP relaxation of the problem and then branch on all of those integer variables until it finds an appropriate integer solution. So let's real quick do that again. Let's get rid of our branch constraint and type in integer there. So now we're solving the integer program, and we see that it spits out the optimal solution we found, 45.0. Which is great. I think there's a way. Oh, I again forgot to swap the screen capture. Yeah, so I changed the category from continuous to integer and solved it and found the same integer optimal solution that we just found using branch and bound by hand. Okay, so that's branch and bound. That's an example of it. Obviously, this is a relatively small problem, and this has a relatively small branch and bound tree. And that took us going on for 35 minutes to do. So if you have a large problem, this can take up a great deal of time. I'm not sure off the top of my head what the time complexity of branch and bound is. Let me see if I can look it up. well, they're exponential. There could be as many as so if n prime is the number of integer variables, there could be as many as 2 to the n different branches you can do at any step. So it's bigger than 2 to the n, or 2 to the n prime, which is quite large already. So it's exponential. It can take a long time to look through a branch and bound tree like this. So this is not an ideal solution to the problem of integer programming, but it's also not our only solution. We'll talk about another version, another idea tomorrow. But it is a very common one. There's one more thing I want to show you with branch and bound, and then we'll be done. Suppose we were on that last sort of iteration, that last branch again. Suppose we were here again, and we found a different solution. We had a slightly different LP somehow, and this branch gave us 3.1, 2.9, something like that. Something decimal. Well, we'd be tempted to branch again and say x, oh well, that's actually not possible. Let's swap this around. Whoops. 2.9, 3.1. X1 well, let's branch on X2 instead. We'd be tempted to say X2 less than or equal to 3, X2 greater than or equal to 4. But doing that adding constraints to an LP. Adding constraints can only reduce the objective function. At any step in this branching process, the branches below, the subproblems below subproblem 6 will never have a better objective function value than subproblem 6 did. They will only ever have 39 or less. So z less than or equal to 39, z less than or equal to 39. Forever, no matter how many branches we end up doing down that path. It will always result in an objective function at least, or at most, 39. But we already found an integer solution that had z equal 40, which is better. It's larger than z equals 39. So we can use this lower bound that we found, and we can already know that none of the branches below subproblem 6 here will be better than subproblem 5. So we can prune that branch. That's called pruning the branch because z is less than the lower bound. So we're only done with branch and bound after every sort of leaf on this tree, that's a graph theory term, every sort of terminal subproblem, all of the most recent subproblems sort of in our branch are either integer solutions, infeasible, or were pruned because their objective function was less than a lower bound we found somewhere else. And that's when we're done with a branch and bound. So it's a slow process. It's systematic, and it will get you your optimal solution eventually. But you may have, if you have, so that's just an example. My research is on redistricting. Our problems have something on the order of 100 integer variables, binary variables specifically. So within binary variables, branch and bound is a little bit easier, but still it's looking at millions of nodes, millions of subproblems on its branch and bound tree. The LP is. And that can take forever. That can take a very, very long time. So yeah. But it will find you your solution eventually, given enough time. It will terminate in a finite amount of time. It might just be longer than you have to live. So yeah, not a great solution, not maybe the solution we want to see to the problem of integer variables, but it is a common one. So that's what I have for today. I'll stick around for answering questions if anyone has any, but you guys are free to go.